Good morning or good afternoon, physics fans. How are we doing today? Sorry I'm running a little bit late today. We will keep things moving though as we go through our notes for the day. I hope everything's going well within your class or within your household. Hopefully everybody's feeling well. Continue to do your little evaluations at the end of each day of notes. I will continue to put little questions up from our notes for that day. I will use that as the evaluation tool. I will also have some problems for you to be able to do eventually as we continue to go through the chapter here. Today we're going to continue to working with fluids. We've talked about water and liquid, water and air are both fluids. We're going to continue to work with the idea of fluids. But before we do that, we're going to talk about what's called atmospheric pressure, because atmospheric pressure, the atmosphere, the air that's around us is a fluid, okay? And we have what is called an atmospheric pressure. This atmospheric pressure is pushing in on our body. So when you're talking about an atmospheric pressure, maybe, it is the pressure exerted on our bodies, exerted by the environment. The atmosphere is around us. We have an atmosphere that's pushing air on top of us. We have a pressure that's put on top of us. Okay? It sort of keeps us, our shape, how we are formed. Without the atmospheric pressure, what would happen is we would probably explode. If you would travel out in space, where you don't have atmospheric pressure, you have to wear a suit. It's called a pressurized suit. If you don't have that pressurized suit, basically you would explode. Okay, and that wouldn't be a good thing. So the atmosphere that we have continues to push on top of us to sort of keep us how we are. The barometer was an instrument, or is an instrument, that's used to measure the atmospheric pressure. An instrument used for the atmospheric pressure. And that is what is called a barometer. Now they basically have all computerized stuff, and they have digital things that are on the wall that can measure that pressure is out there. But the old school way, how they used to do old school way, is the barometer used to be in a dish that was contained. Okay, you had a lid on this dish, or you didn't have a lid on this, but you'd have this dish here. You would fill this tube up and turn it upside down, and then it would lower to a specific level because there was pressure that's being pushed up here that was pushing the fluid back up in there. There was pressure that was pushing down here that would keep the fluid up in this tube here. And that's how they used to measure atmospheric pressure, is the amount or the height that you had there was the atmospheric pressure, because you had you had the atmospheric pusher down, the atmosphere pushing down here and pushing the fluid up into the tube there. Now, standard measurements for pressure. Okay, you have a 1 atmosphere, just 1 atmosphere of pressure. In the SI system, that's 1 times 10 to the 5th Pascals. Okay, that is the standard atmospheric pressure. This is what typically the United States still uses, 29.92 inches of mercury. This is a standard pressure. Once again, these are all standard pressures. These are all standard pressures where everything is just average, basically. The weather systems that we have coming in, we have a high pressure weather system and a low pressure weather systems. High pressure tends to bring us fair weather. It puts more pressure on the clouds and just shoos the clouds away. That's a simple way of thinking about it, shoos the clouds away. We also have pressure volume. You have ideal gas law, that you increase the pressure, you'll decrease volume of what is around also with respect to your air. This column of water, if this is a column of water, it would support 10.3 meters of water. It's pretty tall. 1,013 millibars or 14.7 psi. This 10.3 meters of water, if you were sitting in a pool, and you're down here on the bottom of the pool, and this is 10.3 meters. Okay, what this would result in is you have an atmosphere a pressure that we feel on our bodies right now, if you come down to this level right here, you would feel a second atmosphere pressure because you're 10.3 meters below the surface of the water. Okay? Once again, the pressure that you have would be hard on your eardrums. You'd feel in your eardrums. Weather systems, once again, a high pressure weather system, when it gets high pressure, you get up about 30.5 inches of mercury, or if you get low pressure, you get 28, 27. When it drops really low, that means really bad weather systems are coming in. Hurricanes, snowstorms, blizzards, those are coming in with the low pressure. High pressure sort of shoos all the clouds away and all the bad weather systems away. We like being under high pressure systems unless you want a snow day. Okay, high pressure weather systems mean you're going to get some sunny weather out here. Pascal's principle. Pascal's principle. This is used a lot. If you think about hydraulic lifts, lifting up cars at the automobile shops. They lift up cars. They use Pascal's principle to be able to determine this. Pascal's principle is pressure applied to a fluid in a closed container is transmitted equally to every point on the fluid or to the walls of the container. Okay? You will have equal pressure throughout, not equal force, equal pressure throughout. Pascal, Blaise Pascal, he was also a high-end person in mathematics. He developed mathematic principles, and a lot of those scientific guys back then, they developed both math and science. They dabbled in both of those things. If we take a look at an example, we have 200 Newton force that's being pushed down on a plunger here throughout this, for this hydraulic lift. Okay, this is a very crude hydraulic lift, that's fine. The pressure will be the same throughout. The force, once again, will not be the same throughout unless my areas remain consistent. But if my area here changes, my force that's being pushed upwards is going to change also. So if we take a look, we have a 200 Newton force, we have 2 square centimeters here. 2 square centimeters is our area. Our initial pressure is equal to force divided by area. So we have 200 newtons divided by 2 centimeters squared. So what our initial pressure is going to be is 100 newtons per centimeters squared. Okay, that's the initial pressure. But that pressure will be the same throughout this entire container here. I will have 100 newtons per centimeter squared. Now I didn't change them into meters just because I have square centimeters here and I'll be able to cancel them out. But if I had a newton per meter squared, those are called Pascals. Pascal's principle. Yes, there is a relationship there. So we have 100 newtons per centimeter squared throughout this entire device here. What would be the force coming out? Well, I have 4 square centimeters is my area as I leave. So at the end, we still have to have our pressure equal to 100 newtons per centimeters squared. Well, once again, pressure is calculated by force divided by area. Well, my area at the end is 4 square centimeters. So we have 100 newtons per centimeter squared is equal to force divided by 4 square centimeters. We multiply both sides by 4. My force at the end is going to equal 400 newtons. So I start out with 200 newtons here, and I end up with 400 newtons coming out the other end. So once again, I'm exerting a force. I have a machine that we talked about before that is making life easy for me. As I put a pressure into here, I increase my force over there. Okay, I don't have to exert as much force here because I'm really restricted with my area. Over there, I get more force coming out then. So that's a good thing. Once again, that's how hydraulics work. Types of fluid flow. We have a laminar fluid flow. When it's laminar, you have an even flow where the particles flow, follow the path of the particle, the previous particle. And once again, if I'm going too fast, push pause, and that would slow me down. A laminar flow, if we had a nice little even flow of water or air, whatever, there is just a nice flow of water going through there. There's no bumps in the road, okay? It's like driving on a nice paved new highway or street where it's nice and smooth. You're not going down Burton City Road where you're sitting there trying to go through all the potholes down there on Burton City Road, okay? You have a nice paved road. That's like a laminar flow. But then we have the turbulent flow, which is an irregular flow with interruptions. You tend to have some jagged ideas. Turbulent flow is turbulent driving down Burton City Road. Okay, that road needs to be redone. If we had a pipe that was just restricted here, we would have water that would start flowing or air that would start flowing. Well, what would happen is you would start hitting these walls, and all of a sudden we'd have to start taking right turns and left turns and getting in these people's ways. Okay, what would happen is you start getting a turbulent flow then at that point. When you have irregular flows, that's a turbulent flow. Rapid, if you think about going canoeing, down the Mohican River, going canoeing, when it's nice and smooth, that's your laminar flow. But every once in a while, you get to the raging rapids and you have all those rocks underneath there. You have all those rocks underneath the river. All of a sudden, the water starts getting churned up a little bit and pushing the water up in the air. That's a turbulent flow. Okay, the raging rapids, we sort of enjoy those at times. Got to hang on a little bit, but those are fun to be able to go through the raging rapids. That's a turbulent flow compared to a laminar flow. Eddy, we talk about an eddy. They are physical rapid chains of motion of the fluid. Okay, these, when you have turbulent flow, you're going to have things called eddies. Because what will happen in this case is the flow will start going over here, will hit a wall, and then it will start swirling. And this will start swirling. And then this will start swirling. And then you get these what is called little eddies there. Okay, those are caused by turbulent flow. Oopsie. Ideal flow. No internal friction at all. But ideal flow, not probably going to happen because there's always going to be friction. If we're in a perfect world, we'll get an ideal flow. It's like the ideal gas law. You get an ideal gas. Well, to get us an ideal gas, never going to happen because there's always going to be friction. If there's going to be friction, it's not going to be ideal at that point. But it gives us good guesstimates and predictions out there. Viscosity. It's the amount of internal friction with a fluid. Where you see viscosity, an idea of viscosity like motor oil. Okay, motor oil tries to reduce a lot of the friction with your engine. Okay, so you have to make sure the viscosity is good enough so it eliminates a lot of the heat and a lot of things that go on within your engine. So you have viscosity, it's the internal friction within the flow, within a fluid. High viscosity, honey is high viscosity. Low viscosity, water. And you can also think about things that flow nicely, okay, things that flow nicely will have less viscosity, okay. Honey doesn't flow nicely, okay. So the amount of friction that you have there is going to give you a high viscosity. No viscosity, this is an ideal fluid, but once again, this does not exist. But it's a way that they're trying to try to get to a point where you're cheap. Basically, when you talk about viscosity, you're talking about friction, and to be able to eliminate friction, you eliminate viscosity. The thicker things are, the higher the viscosity is. The thicker they are, the higher the viscosity. The less thick they are, the less you have a viscosity. Friction adds heat to the fluid, dropping viscosity and efficiency of the fluid. Okay, you want a high efficient fluid. Okay, like for motor oil, you want to be able to absorb contaminants within your engine, absorb the heat from your engine to reduce friction, and that's what motor oils does. Is it cools your engine down, helps cool your engine down, and allows it to be able to work more efficiently. And that's what we want to try to do. Reduce the friction, and that's what motor oil absorbs. It absorbs the idea of the bad stuff that happens within your engines. Tomorrow we'll come in, we'll talk about some more types of fluids and fluid flow, what occurs with respect to fluids and Bernoulli's principle, and we'll talk about how airplanes fly. Okay, we'll work with them a little bit and talk about the speed and the pressure of fluids, and that's how airplanes fly. But for today, this will be good enough for today. Once again, go and complete the little exit ticket that I have there for you to be able to get an evaluation in regards to the material that we covered today. Hope everything's going well once again at your home. If you have any questions, feel free to ask. Continue to applaud yourself through the material. Hopefully we get back to some sort of normalcy here. Continue to keep your social distancing. They say it's working, it's doing a good job. So let's continue to push ourselves through this trying time. And I have faith in you guys. You guys do a great job with keeping up with your material and keeping up with the work. So continue to do that. Other than that, adios. I'm out here. You guys have a good day.